Hello, everyone. So now let's finish this section, spanning set. Let's see the example 4. We have P2. So this is capital P actually. P2, that means all the polynomial, all quadratic polynomial, all the polynomial with degree 2. So I'm going to write down like this one. All the vectors like in P2, they are all polynomials. Okay. And all the polynomial satisfy this condition. All the polynomials equals a0 plus a1x plus a2x squared. So you can see the highest order is always 2. This is called the P2. So you know what is P3, right? P3 means the highest power should be x cubed. Degree is 3. Similar thing. Now let's take a look at what's the spanning set for this one. We can see for any vector in this P2, that means for any polynomial is linear combination of what? So any polynomial is a0 times 1 plus a1 times x plus a2 times x squared. So actually any polynomial is linear combination of those 3 things, right? Any vector. For example, you can see 2x squared plus 4x minus 5. Linear combination of x squared, x, and 5 times 1. Is that right? So actually, what's the spanning set? The spanning set is 1x squared is a spanning set. Let's justify the definition. Now let's take a look at the definition 3. So if we put all the vectors v1, 2, n together as a linear combination, then this linear combination gives us like a subset of a vector space V, and we say this is a span set, linear span. So let's take a look at the example. So it's hard to understand from here, right? But if we look at several examples, it won't be difficult to understand. Let's see. If V equals R2 two-dimensional space, and we only have one vector, V1, which is -1, 1. So we want to determine only the span in set spanned by V1, this vector. Okay, let's take a look at this one. So we just write down the new subset as span V1. Span set of V1 means what? All the vectors belongs to R2, and all the vectors is a linear combination of V1 because we only have one vector, so we just write down like this way. And if we continue to plug in V1, what is V1? -1, 1. Let's see. V belongs to R2, so the V vector, any vector in the spanning set is -c and c, and all the c can be anything, belongs to R. So any vector has this kind of form. Okay, and if we look at the graph, R2 means whole 2D plane, and here's x and here's y. All the vector, if we just look at -1, 1, so -1, 1 is here, right? Vector is here, but c can be anything. So that means if c is like a 2, it's become here, this vector. If c is negative, it's become here. So actually c can be anything. This span of the vector -1, 1 actually give us the line. You can see the line is a subset of the 2D plane. Okay, this means the spanning set of the vector -1 and 1. Let's take a look at another example in R3. If the vector space is R3 and we have two vectors, 1, 0, 1, 0, 1, 1. We want to find the spanning set of V1, V2. Okay, so we do the similar thing. Let's write down the span by V1, V2. This equals what? All the vector belongs to R3 now, right? Belongs to R3, and all the vector equals what? Linear combination of C1, V1 plus C2, 0, 1, 1. And simplify. Let's see. This all the vector belongs to R3, and all the vector equals to, just plug in the first component C1. The second component should be C2, right? And third component C1 plus C2. After we simplify. Okay. That is what we need to know. If you want to look at the graph, it's kind of like this is in 3D now, x, y, z, and we have two vectors, 1, 0, 1. So 1, 0, 1 should be y equals 0, x and z both are 1 should be here, this vector. And the other vector is 0, 1, 1, so it should be here. And those vectors give us a plane. Give us a like a kind of plane. So plane is subset in the 3D. Okay, in 3D. Let's take a look at this exercise. If we please find this spanning set V1, V2, if here V1 equals to 1, 2, negative 1, V2 equals negative 2, negative 4, 2. Okay, so here I just give you the solution. This is pretty easy. We can write down this directly. V1, V2, which equals, you can see the vector should belong to R3, and all the vector can be written as linear combination of those two. And after we simplify, all the vector has this form: C1 minus 2C2 and 2C1 minus 4C2, negative C1 plus 2C2. This is the spanning set. Okay, now let's take a look at example 7. Example 7 is the vector space is matrices. Let's take a look. Example 7. We have 3 matrices here. 1, 0, 0, 0. And A2 is 0, 1, 1, 0. You can take a look. And A3 equals 0, 0, 0, 1. We want to find the spanning set spanned by A1, A2, A3. Okay, let's see. Similar to the previous two examples, we write down this as linear combination, and then we can see our new any vector in the spanning set should belongs to similar to R3, R2. Here they are all 2 by 2 matrices, so we write down like this way. Okay, and all the A equals what? C1, like a linear combination of A1, C2, A2, C3, A3, and simplify. A belongs to M2R, and all the A has this form. So if we add those three matrices together, the first position should be C1 at 0, 0 should be just C1, right? And this position should be 0 plus C2 plus 0 should be C2. And same thing, we just add those three together, corresponding components. So it's like C2 here, and here is C3. So you can see, let's spanning set give us what? All the symmetric matrices. Okay, let's give us all the symmetric. Actually, all the symmetric matrices is spanned by those three. Let's see. I think that's all we need to know. And if you want to try, here is the exercise problem. It's pretty easy. Okay, very similar. Find the spanning set spanned by those three matrices. And here's the solution. I'm going to write down this directly. A1, A2, A3 equals to all the matrices belongs to M2R, and all the A equals to, look at the first position, should be A1 plus 0, so it should be C1 plus 3, C3, and this position is negative C1 plus C2, and this position should be 2C1 minus 2C2 plus C3. This position should be C2 at 2C3. So all the matrices has this kind of form. Okay, we can stop this section. Here is the summary of this section. The first thing we need to know is what's the definition of spanning set. So that means any vectors can be written as linear combination. So first definition is like a linear combination, and the spanning set means all spans. Let's see. The vector spans vector space V1, Vn spans V, means any vector in V can be written as linear combination of those vectors. And here the V can be, we learned V can be R2, R3, and maybe matrices can be also polynomial P2 or P3. Right, and we need to know how to prove is there solution or not. For the C1, C2, C3, there's a solution or not. If there's a solution, means the linear combination exists, then they span. And then we learned definition of C1, V1, Vn, like this. Just write down this as linear combination. C1, V1. And we have several examples, like 4, 5, 6. Okay, that's all we need to know for this section.